Okay, good morning, afternoon, or evening, everybody. Welcome to the Examining Hurricane Milton's Milestones with NASA's GES DISC Datasets ESDIS Data Training webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Time, so we are going to go ahead and get started here. What I'll do first is begin today's webinar with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or questions, please enter them into the Q&A panel rather than the chat, and you should see that on the right side of your screen. If you don't see that, then click on the three dots at the bottom of your screen. Let me do a quick audio check. Is anybody experiencing any audio issues? If you could type into the chat before I continue forward. Can you hear me okay? It's fine? Okay, perfect. Okay, perfect. Let me continue forward here. Excellent. Thanks so much, everybody. All right, so if you can't see the Q&A panel, what I'd like for you to do is click on the three dots at the bottom of your screen, and that will pull up your panel options, and you can then insert a check mark next to the Q&A panel. Today's webinar is being recorded. The recording will be posted to our NASA Earthdata YouTube channel within a week of completion, but generally I would say it only takes me a couple of days. Once completed, I will send an email to all registrants and participants that includes both the links to the recording as well as to the presentation slide deck used within today's webinar. As far as timing is concerned, today's webinar will be 1 hour and 15 minutes long with an estimated 45 to 50 minutes allocated to the presentation and live demonstrations and a 15-minute question and answer period to begin after the presentation. Depending on the volume of questions received, we may extend the Q&A session, but we will have a hard cutoff of 3:15 p.m. Eastern Time. During today's webinar, we have 3 speakers and 2 Q&A panelists. Our first speaker is Dr. James Acker. Dr. Acker is a senior support scientist at NASA's Goddard Earth Sciences Data and Information Services Center, or GES DISC. He will begin today's webinar with an introduction and context for the development of Hurricane Milton and the storm's milestones. From there, we will transition to our second speaker this afternoon, Kristen Morgan. Kristen is an atmospheric scientist, also at NASA GES DISC. She will provide an introduction to NASA's TROPICS mission, use cases for TROPICS data, and will showcase specific TROPICS data sets that can be used to investigate Hurricane Milton and tropical cyclone development. Once she finishes, we will toss it back over to Jim, who will discuss the water impacts on Florida from Milton. From here, we will transition to our third speaker this afternoon, Chris Battisto. Chris is a scientific software developer at Goddard DAC. He will conduct a live Jupyter Notebook demonstration using both OPeNDAP and the earthaccess Python library to show you how to work with these data that have been showcased in today's presentation. After Chris is finished with this demonstration, we will transition to a quick wrap-up, and from there, we'll move directly to the optional final polling questions and the Q&A session. Let me actually advance my slide here. All right, we have 2 Q&A panelists during this afternoon's event. Dr. William Blackwell, who is the principal investigator for the NASA TROPICS mission, and Dr. Vince Leslie, an instrument scientist also for the TROPICS mission. They will be available during the Q&A session at the end and also throughout to address any of your questions in the Q&A panel. Before I toss it over to Dr. Acker, I just wanted to say a few words about this afternoon's Q&A session. We will try to address all questions during the Q&A. However, if we do not get to your question during the webinar, our speakers will be able to follow up with you offline. And so with that, it is my pleasure to introduce today's first speaker, Dr. James Acker. Dr. Acker, and then with that, I'm going to stop sharing my screen and toss it over to Jim. All right, so Jim.
Hi, can you hear me?
I can hear you very well, thank you. You should have presenter privileges at this point.
Let me share my screen.
All right, I can see your screen. It just needs to be in slideshow mode. There you go.
Okay.
Perfect. Thank you.
Thank you, Jennifer. And welcome to everybody who's watching and listening in. As Jennifer said, the title of our webinar today is Examining Hurricane Milton's Milestones with NASA's GES DISC Datasets. And we'll get right to it. Why look at Milton? I mean, Hurricane Milton had literally several milestones. You can see at the top a timeline of the existence of this storm. It had the fastest intensification ever observed, 35 miles per hour as a tropical storm to 160 miles per hour in 49 hours. It was the fifth most intense Atlantic hurricane on record with a central pressure of 897 millibars at its most intense. And it spawned 45 tornadoes in Florida, at least, when it hit the peninsula and dissipated, and all that spinning energy spun off into tornadoes. It also caused a lot of rain in Tampa and the Pinellas County and western coast areas of Florida where it came inland. Tampa International Airport received about 12 inches of rain. St. Petersburg, right next to my graduate school, saw nearly 19 inches, which was a record for the month. And as we said, it spun off a lot of tornadoes. Therefore, it caused a lot of tornado warnings, more than 100 in the state. So it was a very significant storm. And if you were watching as it hit land, it was very frightening for a lot of people. So, as we said, it started out as a tropical low pressure system west of the Yucatan Peninsula. Almost immediately, it was recognized that it was going to be a dangerous threat to the state of Florida. And we are going to show you several different data sets that are available at our data center, the GES DISC, and data from the TROPICS mission, which was almost specifically designed to look at rapidly intensifying hurricanes. So Milton was perfect for this. And we'll look at it, why it was so remarkable and such a record-setting hurricane. So a quick look at the agenda. We have the context. I'm going to look at the oceanographic environment that spawned it, a little bit of what Milton did, where it went, where it started, where it went, and some after effects that we observed. Then we'll talk about the TROPICS mission and why this data is so useful to look at tropical storms and hurricanes, a little bit of the water impacts, and then, as Jennifer said, Chris Batista will show how to use Jupyter Notebooks to look at the TROPICS data and what you can learn from it. So, Hurricane Milton, it was a disorganized, big area of clouds west of the Yucatan Peninsula and near the Mexican coast. And as soon as it started to form, weather models indicated it was likely to intensify and would become a serious threat. The next couple of pictures are taken from the NASA Worldview, which is a great way of looking at events in the atmosphere and on land. And the data is from both the moderate resolution imaging spectroradiometer MODIS, and also some images are from the visible infrared imaging radiometer suite, also called VIIRS, on the SWOMI NPP satellite. So we saw what it looked like as it was disorganized. It rapidly organized. 2 days later, very clear tropical cyclonic circulation, still west of the Yucatan Peninsula, but starting to move eastward. And then 2 days later, as it became very intense, it was north of the Yucatan Peninsula. You can see in this slide from SWOMI NPP, it was also stirring up deeper water. You can see some sediments on the Yucatan shelf that were stirred up over here, and a very well-formed eye on the 8th. Then it accelerated, moving across the Gulf, fortunately losing a little bit of intensity, and then it made landfall. It was fortunate, a very fortunate landfall for this powerful storm, because it came in just south of the mouth of Tampa Bay. Had it come in at the mouth or a little bit north, the storm surge in the bay would have been much larger and more destructive. So that was fortunate, and it also lost a little bit of intensity. It went from a category 5 at peak strength down to a category 3 at landfall. It went straight across the peninsula, spinning off tornadoes, and it was gone the following day on the 10th. So these are two plots showing the history of Milton in terms of its wind strength, its intensity. The plot from Moody's live blog shows the wind track and the width of the wind track. And you can see I'm pointing with the black arrow to where the peak intensity sustained winds of 167 miles per hour were seen. Again, right next to the Yucatan Peninsula, which is significant. And you can also see on the right the intensity track. And this was from the IBTraX dataset. You can see how quickly it intensified from yellow to orange to red to magenta as it intensified from tropical storm into a Category 5 hurricane. And this is the iconic image of the destruction. This is the Tropicana field where the Tampa Bay Rays used to play baseball, not this season. And the special fabric roof was supposed to stand up to 110 mile per hour winds. Peak strength was 106 miles per hour, but it didn't quite meet the specs. So why was it so favorable for Milton to intensify? What I've used here is our Giovanni system, and I've taken plots of the MERA 2 ocean surface skin temperature, which in most parts of the world is also just about the same as sea surface temperature. Slight differences, but not significant for us. And I used Giovanni to make a average plot of the temperature for the 10-year period, 2014 to 2023. And then I also made a plot for September 2024. And using the NASA Panoply software, I subtracted the average from the September 2024 data, and the plot you see on the right is the differences. And you can see it was significantly warmer, pretty much over the entire Gulf. In the September 2024, and the arrow points to where it was the warmest. And this was probably at least a degree, maybe up to 1.2 degrees centigrade warmer than the average. And this is where Milton gained its highest intensity. And that was something that was very clear in both the imagery and in the data. And then I had actually thought, hey, Milton was an October storm, so let's look at the October temperatures. I actually did this first before I did the September temperatures, and I saw something that initially surprised me, but was fairly easy to explain. And so I did the same thing with a 10-year average and then the data for October 2024, and I noticed it was cooler. Okay, and when the difference map was plotted with Panoply again, okay, you can see that over the entire Gulf, and this is monthly data, I'll say something about that. Okay, it was cooler, particularly in this area of the Eastern Gulf right near Florida. The reason for this is that many people know this. If not, hurricanes stir up water from deeper waters that are cooler. Okay, so Milton, as it passed over the Gulf, stirred up water from deeper that was cooler, and it left this imprint. Now, the Gulf was not cooler the entire month. At least I doubt it, because the sun was still shining. But because this was such an anomaly for the entire month, it shows up clearly as the footprint of Milton. Okay, and I believe we're going to move on to our next slide. Right, so I'm going to stop sharing. You'll see this same slide from Kristen in just a moment.
All right. Thank you, Jim, for that great introduction. So I am the lead data curator for the TROPICS mission, and I have the pleasure of introducing the diverse data products that the mission provides and we archive here at the GES DISC. So TROPICS expanded is the time-resolved observations of precipitation structure and storm intensity with a constellation of smallsats. And so the image on the right is taken from the TROPICS mission homepage, sponsored by MIT Lincoln Laboratory. So you can see the constellation of 4 CubeSats in low Earth orbit that provide high resolution coverage of the TROPICS area. And the constellation provides passive microwave radiometric measurements within 12 bands. I'll restart this. Great. And I will expand upon the 12 channels. And the benefits of using CubeSats rather than traditional single payload satellites is the CubeSats have a lower development cost and certainly a shorter development time. Additionally, they're lighter for launches into orbit, and so they are great candidates for shared rides into orbit as well. And so the TROPICS mission provides users with a high-resolution, low-latency suite of observations of this critical tropical cyclone in data. I have to pause it. Perfect. So here we have a table of the various data products that we receive from the TROPICS mission, sorted by level. And our co-speaker, Chris Battisto, later on in the presentation will really expand upon the nuances between each data level. And so for the purposes of my portion, I'm going to be sharing plots of the grade portion of the table, level 2A and level 2B products. And so we have unified resolution brightness temperature that provides resampled brightness temperatures with meteorological applications, including relevancy to forecast modeling. Additionally, we have precipitation retrievals and profiling schemes that give us rain rate so we can understand the rainfall when a tropical system makes landfall. Additionally, TROPICS enables us to look at the storms from a vertical perspective, giving us temperature and moisture vertical profiles, as well as total precipitable water. So we can really analyze the thermodynamic structure of tropical cyclones. Finally, the final level 2B product that I'll be sharing is the cyclonic intensity estimate algorithm, which gives us minimum sea level pressure and maximum sustained winds to allow us to evaluate the strength of the tropical system. And below, I have a display of the 12 channels that the TROPICS sensor uses. So from left to right, we have channels 1 and 9, which give us precipitation retrievals and scattering responses. Channel 12 is really useful for identifying and classifying ice particles. And finally, channels 2 through 8 give us our temperature profiles and help delineate precipitation from its liquid and frozen state. So starting with the level 2B, level 2A brightness temperature in degrees Kelvin, we can look at the cyclogenesis of Milton. So the image on the left is observed on the 6th of October when Milton was observed in the Gulf and still developing into a tropical storm. And on the right, the image we have is from the 2 days later, October 8th. And we can see the difference in the two plots where Milton rapidly intensifies to a category 5. Certainly on the right, you see a very clear eye wall replacement cycle happening and a clear eye forming. And so just to explain what brightness temperature physically means is excuse me, this is a sort of the anatomy of a hurricane, and you can see near the surface you have warmer temperatures, and at height you have cooler temperatures. So this is really beneficial to look at sort of the height of the storm, which corresponds to the strength of the storm. So you see these warm temperatures here at surface, and you see this very tall, very strong Category 5 cyclone. I have hyperlinks to the specific data sets that were used. On the left, this is CubeSat 6 that observed Milton here on the 6th. And on the right, you have CubeSat 3rd that observed it on the 8th. And these links and much more will be provided near the end of the presentation. And so moving on to the level 2B product, the MERS product, we're looking at vertically integrated water vapor as a signal of Milton's intensification. And so as Milton is traveling over these anomalously warm waters in the Gulf that Jim did a really great job demonstrating, the TROPICS 6 CubeSat observed increasing water vapor content in the outer rain band. So you can really see the total precipitable water in units of millimeter. You can see this really heightened signal here as Milton at its peak strength is heading towards the western Gulf of, the western coast of Florida. And so Milton will end up sort of carrying this precipitable water as it heads to landfall in Florida and unleashes sort of catastrophic rainfall. And this is a really, really powerful slide in terms of looking at the structure of the cyclone, the vertical structure of the cyclone. So let's start down here at the bottom right. Again, we're looking at surface up to height. And so you're seeing these sort of warmer colors corresponding to the surface, and the cooler temperatures are at height. For the image on the right, this is again taken from TROPICS, the third CubeSat, on the 8th of October as well. So you can kind of see the temperature signature as you look at it vertically. And then additionally, you can look at the water vapor mixing ratio vertically from surface to height, which really demonstrate, these data sets really allow us to look at the anatomy of the specific storm as well, which can be really powerful for analyzing and evaluating the strength of the cyclone. And then we have the level 2B precipitation product. We're looking at rain rate. And so we're looking here at the 9th of October, which is just the beginning of landfall. You'd probably say landfall more squarely happened on the 10th. But here on the right, you can see this inner core rain rate maximum of about 1 inch per hour as Milton headed to Florida's west coast on the 9th. And remember that at this point, Milton had lost a little bit of steam, if you will, and was downgraded to a Category 3 hurricane. But the significance of it was that it was still holding a lot of water vapor, a lot of precipitable water that was ultimately precipitated over Florida. And then a Florida State climatologist, Dr. Powell, wrote up this really wonderful post-storm summary report of Milton. And this image was taken from the National Weather Service in Melbourne, which is right here on the eastern coast of Florida, which depicts the total rainfall of the storm from October 9th to October 11th. And so you can see this really distinct band of intense rainfall across Florida's panhandle. And you can see here, very identifiable areas of Florida, including Tampa and Orlando. And again, this is where the Weather Service was as well. And I will pass it back to Jim.
Hi again. Okay, so I'm going to just take a short look. We did the previous slide just showed the rainfall from Milton as it came onto Florida, and we have a data set at the GES DISC called the North American Land Data Assimilation System dataset, and there's also a global dataset they are called NLDAS and GLDAS for short. And this is a system that provides a great deal of different hydrological variables. And you can look at numerous different aspects of hydrology. You can look at soil moisture, and it also has some rainfall products. But one of the things that I looked at for Milton was surface runoff. Okay, now surface runoff you can see in many different cases. You can see it vary as the snow melts in the mountains in springtime. But for Milton, as Milton came on land, it was an intense storm carrying a lot of rain, as Kristen noted, like 1 inch per hour. And so as soon as that rain hits the ground, it turns into runoff. And so you can see a real core as it came on land right by Siesta Key and Longboat Key, came inland. And so here's the peak of rainfall at 18Z, that's UTC time, on the 9th. Okay, and then it moved across and north following the track, and so the runoff then started to hit in the north central part of the peninsula, and this is on the 10th at 0.01Z. Okay, and then finally you can see as it was exiting, it dropped a lot of rain on the east coast, right near where the St. Johns River, which goes up here toward Jacksonville, originates. And so this was the last look, if you want to say so, for Milton at 18Z, and that should be on the 10th, not the 9th. So the next thing to look at is where the surface runoff goes into in the streams. And this is where it starts to get significant for flooding. Okay, and so this is another NLDAS variable called streamflow. And so you can see at 18Z on the 9th, Milton has just basically arrived and is dropping rainfall. And you can see the various intensities. And this is the Apalachicola River, and this is the St. Johns River. And there are several small rivers that drain into Tampa Bay, so keep an eye on that. I circled this on the next slide. You can start to see this area, the stream flow is increasing. Here's the scale, which is in units of, meters cubed per second. So this is the stream flow in cubic meters per second. And then you can see it start to pick up compared to here. And then just a few hours later, remember there's going to be a lag time, it has intensified quite a bit. You can see in the headwaters of the St. Johns, much heavier, and you can also see several of the streams flowing back into Tampa Bay. So Milton drops rain, you get that flooding, and then you get the streams starting to jump out of their banks. And so one of the ones I looked at, it's a small river called the Alafaya that drains into Tampa Bay, and it really, these 3 pixels of the data encompass most of the Alafaya watershed. It goes in maybe a little bit over here too. And so you can see how it picked up, how it was draining right back in there. And this is a drone video taken of, near the Alafaya River and some of the flooding. You can see several houses here were almost completely inundated. And the final thing to think about, which you could watch in the NLDAS data, is that the stream flow, this flooding sticks around for a while because Florida is very flat. And so you can watch how long the stream flow persists, and that can be quite significant to recovery efforts and people, getting back to their houses and starting to try and recover from a disaster like Milton. Okay, that's all I have, and so we'll now switch to Chris Battisto.
Let me go ahead and share my screen. All right, well, thank you, Jim. So you all just saw that there are definitely multiple ways that you can visualize and access some of our data, but one way that you can have a little bit more control over it is by using Python with Jupyter Notebooks. So Python is currently one of the largest supported geospatial analysis tools that are out there, with numerous open source libraries, some of which are ones that us at GES DISC are contributing to. And so what you can do is you can show users how to programmatically access the data to perform any sort of analysis that they want. But today we're just going to show how we accessed some of these granules, or what we call granules, for some of the collections that you saw, focusing on the TROPICS collections in some of the plots that Kristen showed earlier. And so Jupyter Notebooks, and I'm gonna, if you could all please just bear with me through my speed here. We've got quite a bit of a lengthy Jupyter Notebook, and so I ask everyone to be patient with that, and if they have any questions, please feel free to reach out to me at my email or in the Q&A panel afterwards. But we're going to be using this Jupyter Notebook in Google Colab, which is provided for free by Google, to grab all of our granules of interest from a service called OPeNDAP, and from our public cloud endpoints. And we'll also be showing how to get those links through the Earthdata search tool. So there's going to be 3 different tools in here, but all of them are tailored specifically for analyzing level 2 data like you see here with TROPICS. And the best part of it, in my opinion, is that we try to make it as analysis ready as possible, meaning that there is no downloading needed. So all you need to do is click a link to a Google Colab notebook. You can run it as long as you have a Google account and a NASA Earthdata account, both of which are free. And you can run your analysis and change the spatiotemporal queries of some of our things at your discretion. So we're going to be showing in total 4 different TROPICS collections. We'll be showing 1 URAD collection, or excuse me, 1 granule from URAD, 1 granule from PRPS, and 1 granule from MERS. And then we're going to be showing about 95 granules from TCIE. I'll get into why we're doing that in a bit. So a couple more notes about what these data processing levels represent. You saw Kristen share earlier this table showing the processing levels and the variables next to them for the TROPICS collection. Knowing what the data processing levels are for NASA Earthdata is one of the most critical pieces of information that anybody who accesses our data should at least have a loose understanding of. And that's because different levels of processing will require different levels of manipulation depending on the tool that you're using. It also gives you more control potentially over the quality of the data that you are displaying. So you see on the left, we have starting with level 0, which is basically just the unprocessed raw data coming down from the satellite. And then once it gets into level 1, and you can see that split into A, B, and C, that's where we start to basically attach time variables, latitudes and longitude variables, and that's also where we start to write units and attributes to the actual files. So level 1 data is typically for a lot of these radiometric and georeferencing parameter variables and data sets. But once we start to get into level 2, we start to get into products that have some derivations. So for example, surface return elevations, ground elevations, and that also can be used to provide different variables like pressure or brightness temperature that are resampled with height, which is what we're showing with URAD. And so I've highlighted in this blue rectangle on the right the level 2A and 2B types of processing levels for the TROPICS collections that we're going to show. And you can see that the level 2B data set is similar to the level 1B data sets, which are basically that they have instrument units processed. And all the other collections that we have are level 2B. The other collections with the higher processing levels, specifically around level 3, is where you start to get into things that look a little bit more intuitive. So these are usually attached to a grid, and there's been interpolations and spatiotemporal adjustments with a little bit of completeness. Some of them might cover the whole planet, some of them might not. The two most popular collections that we host at GES DISC are the two most popular level 3 collections are Meritu and GPM. And then you start to get into level 4 collections, which actually use model output to fill in any of those other gaps. GES DISC actually does not host any level 4 collections, but other DACs do. So how is this level 2 data structured in this analysis specifically? Well, level 2 data can have a few different file formats or granule formats, usually in GIF, NetCDF, or HDF. HDF is, of course, underneath the NetCDF library. But what you will notice with all of these is that it's not as simple as accessing a file and seeing that it has a time dimension, a latitude dimension, and a longitude dimension like you might be used to with some of our level 3 collections. Instead, for TROPICS, we have this swath, and the swath actually traces the path of the satellite as it traverses the globe, wherever it may be for that particular point in time, taking its measurements. And so the X and the Y of this are referred to as the along track and the cross track. And it's not even an X and a Y. Sometimes the path can be, a little bit diagonal, or not necessarily just with how this is structured, being on a sphere. And so you have the satellite that goes across the swath, and in this case for TROPICS, you have a 2,200 kilometer long swath. For TROPICS, that takes about 1.5 hours to traverse. So you will see that the granules are structured with a start and an end time that is about 1.5 hours long. And then along that path, you get this scan space, which for these collections is about 15.2 kilometers wide. And inside of each of those scans, there are these spots. And inside of a scan, the nadir spot, which is looking directly down in the middle, is the 41st index. So you will see that when we open some of these collections, you have these dimensions that may look unintuitive. So you may see time kind of buried in the attributes, or you may see dimensions that represent quality control flags. We will show you all how to deal with those and how to turn that into something that makes sense for you to use in your analysis on your own. And so I just also want to reemphasize that this data is not gridded. So if you were to try to compare this to, let's say, a level 3 or 4 collection, you will notice that there is no latitude or longitude in the coordinates to easily interpolate it to. And that's because what you have to do is take those latitude and longitude arrays that are inside of them to construct a rectangular grid of some sort. Because all that does is it stores the along track and the cross track rectangle of basically where those latitude and longitude scans are. So that is just something to keep in mind with this level 2 data. And then you get some variances between collections. In this case, in both CubeSat 3 and 6 for TCIE, which is the tropical cyclone intensity estimates, there may actually only be 1 point inside of those. And so you need to know what each collection and what each variable is structured like by consulting the user guides. This is a critical step to understand how to open and view these level 2 collections. But the benefit with those is that we get these quality control variables. And so you'll see quality control variables in a few of our other level 3 collections, including GPM. But what these are important for is to filter out any sort of artifacting that might have occurred in the reprocessing of the data as it is filtered through those processing levels. Or there could even just be artifacts based on the fact that this is a sensitive instrument, floating around, and it may get hit with radiation at some parts that might distort some of the variables, for example, brightness, temperature, and some of the different bands. So these are all just things that we can have a tolerance for, and we can actually adjust that tolerance. And then again, the final bullet point, just make sure you read the manuals and the READMEs and the user guides for each of these level 2 collections. So here's our workflow for this Jupyter Notebook. It is quite a long Jupyter Notebook, but you will see that we've done our best to kind of lay out what is happening in each of the different steps. So what we do is we use a library called earthaccess, and we use the Earthdata search web tool to grab these granule titles for the collections that we are interested in. So we're going to do that using the web interface for the 3 URAD, PRPS, and MIRS collections. And then we're going to simply just use a bounding box to query over the length of Hurricane Milton for TCIE. But what we're going to be doing this for is using a bounding box in the web tool in order to see which paths and which swaths passed over our area of interest. Because keep in mind that these are not covering the entire globe. It is literally just CubeSats orbiting a path, and there might not be coverage for a particular date and time that you want. So it's important to see using some of the tools that we have, like Earthdata search, to find your variables of interest and your files of interest. Once we get those, we will create our OPeNDAP subset URLs. And we're going to use OPeNDAP to access the variables of interest from PRPS, MIRS, and URAD. OPeNDAP is something that I'll get into a little bit as we get into the Jupyter Notebook, but it requires us taking these URLs for where the data is stored, finding where the OPeNDAP service links are, and then appending these variable subset constraint expressions to them. Once we do that, later in the notebook, we will show how to access and combine the TCIE collection data. And so we're going to query both CubeSats 3 and 6. We will show how to combine all those granules together into a single combined data set and then sort it with time. And through that, we're not going to be using OPeNDAP. Instead, because those granules are so small, we're just going to stream the entire granule using earthaccess and Xarray, which will be coming from our public Earthdata Cloud endpoints. And then after that, you will wind up with 4 plots in your Jupyter Notebook, kind of organized by time. So we're going to demonstrate the URAD brightness temperature just after Hurricane Milton hit peak strength. around 0Z on October 8th. For mirrors, we will be showing total precipitable water to just show the amount of moisture that Milton carried as it headed towards the Florida coast. And then we're going to be showing our PRPS precipitation rates, which are in millimeters per hour around the time of Florida landfall. Again, this is the same plot that you saw earlier shown by Kristen. And then an extra plot that you didn't see is that we're actually going to take all of those TCIE variables, which show max wind and mean sea level pressure. And we're going to plot how those change with time. And you will actually be able to see Hurricane Milton strengthening and weakening over time, being able to see pressure drops correspond with these big spikes in maximum derived winds. And that's from October 6th to the 14th. So with that being said, let's go ahead and get started into the demo portion of this webinar. You do not have to follow along with me in real time. I'm just going to be simply clicking each cell as they run. But in order to run this with me or to run it in the future, you need both a Google account in order to actually access the Colab runtime, which is free. And then you will need an Earthdata login account. And so to create an Earthdata login account, there is a link at the bottom of this slide, which I can certainly, or if someone else could, share that in the meeting chat. And then all you need is a valid email to be able to do that. So you can pick any username or password you want. You don't even have to put your real name in it, but it does need to be connected to an email that you can have access to validate it. There's a couple of different steps that also need to be followed to ensure that you can access data from our OPeNDAP endpoints or from our cloud data endpoints. That's also in that guide that is posted in the last bullet point. You will see that once we open the notebook, the first thing we do is authenticate with the the Earthdata login servers. This is required to just access the data and download it at any point. And so we're going to be using a token and a netrc. The netrc will store your username and password, but not to fret. This runtime is temporary. So everything that will be running in this notebook will be deleted at some point. For Google Colab notebooks with the free tier that we're using, you get 90 minutes to restart the runtime if you wish after you close the browser, or if you leave the browser open, it will stay active for about 12 hours of idling. So let me go ahead and exit full screen from the presentation. And I'm going to copy the link for the Jupyter Notebook, and I'm going to see if I can post a link to it in the chat.
We can take care of that for you.
Okay, wonderful. Thank you. And then what I'm going to do is I'm going to simply open that link, which you will also see this Open in Colab button inside the Jupyter Notebook. And it's going to open up a tab in Colab. So what this is doing is it's pulling this webinar notebook from our GES DISC tutorials repository, which is a public GitHub repository that houses dozens of other Jupyter notebooks to access and analyze different collections. And we can use Colab to pretty much open any of those that we want. The only difference is that some of the libraries that are included by default with Google Colab might not be installed, and so we will take some steps to install those at the beginning. So when you are all logged in and you have your Earthdata login account and you're ready to run this, you will be met with this interface. And this interface is pretty much the same for any other interface for accessing and running Jupyter notebooks. You basically have these cells containing markdown and containing code. And you can see that the code cells have this little play button to the next to them versus the markdown. Markdown, however, contains a bunch of different links that you can use. And this is great because not only can you post code, but you can see the output of that code as it is run. And that is really important for a lot of scientific analyses, particularly as it pertains to geospatial data. So in this notebook, you can see that we list all of our prerequisites. these are all of the different libraries that we'll be using. We will be using a library called earthaccess to parse through our links. We'll be using Xarray to open from the public cloud endpoints. We'll be using OPeNDAP, which is the library developed by the OPeNDAP team to access our OPeNDAP collections. And then these other libraries, matplotlib, cartopy, numpy, pandas, these will be used to do various things like date formatting, manipulating some of the arrays, and then for the actual plotting. These are all libraries that are very, very widely supported and have lots of development going into them. So let's go ahead and get started. So the cells will run in the order that you click them. What I'm going to do here is just click on the cell that I want to run. In this case, I'm first going to install the packages and the libraries. You might get prompted that this notebook was not authored by Google. That's perfectly fine. You will click run anyway. And then it's going to connect to the Google Compute Engine, to the shared runtime, which is basically, it's almost as if we're running off of someone's rented computer here that only runs Jupyter notebooks. And it's going to install the OPeNDAP, the earthaccess, and the cartopy libraries that are not included by default. This will take about 30 seconds to run. Once we do that, we can go ahead and import all of our libraries. You can see that there's a couple of libraries that are in there built into Python that we don't need to install. But this is the first step that we do whenever we run Python code. So I'm going to go ahead and press the run button there, and that will run once all of our libraries are installed. You'll see that this pip dependency resolver error shows up. That's not an issue. And now we can import all of our libraries. So the first thing we need to do is create this token to be able to access the data from our Earthdata login servers. And so we use this code block here, which will create a token that will be stored in your Earthdata login account, even if it doesn't exist. So you need to all know your username and password for this, and then we're actually going to do this again later in the notebook. So when I run this, near the bottom, it's going to prompt me for my EDL login and password. A quick note, it does not check if the username and password is correct or not. So please be careful when you're typing this in. If you get an error later in the notebook related to an unauthorized access message, feel free to just run this cell again, and it will overwrite the token that is stored. So let me type in my username and password. A bit of a typo there. And when I run that, I see that I retrieve my token successfully and I store it in memory. That will be wiped when this session is ended. Now we can actually search for the granules of interest. So with the level or with the nature of these level 2 collections, for the URAD, the MIRS, and the PRPS plots that you saw earlier, what I want to do is just kind of manually sift through what is in there over the time and the bounding box that I want. And I'm just going to grab the actual granule URL from the Earthdata search results. And so what I've done is included links to these here. And so I'm just going to click on one of these just to give you an overall gist of what it looks like. But the Earthdata search tool is basically a graphical user interface for the content metadata repository. And that is referred to as the CMR. So what that basically is it is this giant repository containing the metadata for every single NASA Earthdata granule. And within that metadata will be things like OPeNDAP links or variables or various attributes or the areas that the granule covers. So when we do this, when we get our links and when we run it in the Jupyter Notebook in with those Earthdata search queries, it is not, I repeat, it is not the same as a subset where we are actually accessing them. What we are simply doing is seeing if the granule is over this spatiotemporal area of interest. And if it is there, we will get a response of the metadata of those granules from the CMR repository. And you will notice that that cell that we run later only takes about 4 seconds. And it does not take 4 seconds to access most of our collections, even if they're small, especially from OPeNDAP. So you can see on the left here, I've got my collection short name that I have entered, along with the bounding box and the temporal query. And you can see the blue bounding box over the north side of the Yucatan Peninsula, which is around the same area and time that Hurricane Milton experienced 2 eyewall replacement cycles. And what I've done here is I've selected the granule that I want, and when I hover over it on the left here in this grid, you can see the start and the end time, and you can even see a preview thumbnail here, which is really useful for level 2 data, just to see that the data is looking good and then it's over the area of interest, along with kind of a range of the magnitude of the to basically see what I can make my color bar for once we get into these plots later. So when I find the granule that I want, I can click on these 3 dots in the top, and then I'll click View Details. And then you're met with this real long metadata JSON response. But all I want for this particular instance is this title attribute here. And so I've already copied and pasted these into the Jupyter Notebook. And so once you get those for your PRPS, your MIRS, and your URAD, you can query them with Earthdata search. Another option is you could simply just parse through this and grab the links that you want. Here's a bunch of links, including the OPeNDAP link. But we can do that programmatically just in case these links change. And that's always best to not hard code things like service URLs. So let's go ahead and go into our other tab back to our Jupyter Notebook. And in this cell, you can see that we've got our 6 different queries, our 5 different queries. And the only difference is that you've got the granule URL for the top 3, and then for the bottom 2, for our TCIE collections, we do include the bounding box and the temporal times. So these 2 results here will be much lengthier than these 3. These will just give you 1. So I'm going to click Run, and you will see that this only takes a few seconds to run. And I've now stored the results of all of that metadata in my, my notebook variables. So now let's go ahead and parse out our OPeNDAP variables. For each of our collections that use this OPeNDAP service, and you can tell if it uses that by visiting the dataset landing page for each collection, you can drill down through a user interface to see all of the names of the variables that are included to be subsetted. And what you can do is you can create these URLs using this OPeNDAP service to basically access those variables from a multitude of different tools. The only difference is that the URL subsets may be formatted slightly differently for some tools rather than others. And I've included some notes about that here. For example, if you want to download them using requests, the constraint expressions are different than in this notebook, which uses PyDAP. And so you can see here that what we do is we filter through those responses, we grab the OPeNDAP link, and then we parse through and attach the constraint expressions containing the variables that we want. So you can see that for URAD, we have brightness, temperature, rain rate for PRPS, and we do that 3 different times. So let me go ahead and click Run for each of these cells. Something else to note is that if you were to click on these links here, you're going to be met with an error, and that's because these links are designed for PyDAP and not for downloading through the browser. So I run that 3 separate times, and now I've got all of my OPeNDAP links, so I'm ready to finally start my analysis. So before we plot every single collection that you see here, the first thing that we need to do is actually load it into our session using PyDAP. Once we do that, it'll go ahead and print all of the variables, which means that the metadata of this has been loaded into memory. And now we can start our analysis. So for each of these, and I'm just, again, with the sake of time, I'm just going to very briefly go over what's going on in each of these codes. First, we select the channel and the band, which represent these different parts of the storm or the scan that we want to look at. In this case, we're looking at the 12th channel and the 5th band, which correspond to the upper part of the hurricane for our brightness temperature variable. Then what we do is we load all of those into variables, and then we parse through all of them to perform our quality control filtering. So for TROPICS, for some of these collections, there are these bits in this QFC variable here called cal quality flag. And what we can do is we can set a tolerance for seeing how many bit error flags that there are. And so these bits 2 through 5 represent different data quality control flags, some of which might be related to maybe a negative value where it should be a positive, or a missing value, or even maybe some sort of artifact from when the measurement was taken. And so for some of them, you could have a higher or lower threshold than others. For URAD, we're going to be a little bit more liberal with that. And we're just going to say if there's more or 2 bits flagged, then we will write not a number to it. So we go through every scan and spot in that scan and perform that. And then once we do that, we perform a couple of other routines down here to make the actual plot. And when I run this, and it should only take about a few seconds here, it is going to load all of that data from OPeNDAP. It's going to extract them. First, you'll see that it's downloading some Cartopy shapefiles, and then you'll see your plot without having downloaded anything. And so we wind up with our first plot here, which is our URAD brightness temperature, a little bit zoomed in from the plot that Kristen showed. But in this one, I really like it because you can even see the definition of the eye wall. And this is taken just around the time of the peak strength of Hurricane Milton. Moving on to our plotting derived rain rates using PRPS. We repeat the same process. We first load the data from our OPeNDAP query into our notebook session. And then we open up all of our variables that we want. We go through these quality flags. And if in this case, there's only one quality flag, then we write it to not a number. So we're a little bit stricter about the quality controls here with our PRPS plot. And then we wind up with a slightly more zoomed in plot of the one that you saw Kristen show earlier, with rain rates approaching nearly 25 millimeters per hour. It's just an amazing amount of rain. And then finally, for these first 3 single plots, we will look at our total precipitable water, which goes through the entire column of the hurricane. For this one, you'll also see that there's a scale factor inside of this TPW variable. And so what that means is you need to multiply that by the scale factor, or else you'll get units that are off by a magnitude. And then here we have the same quality control leniency that we do for URAD. So let me go ahead and run this here. Something else I want to also note is that sometimes for Earthdata login authentication, you will get the metadata to load. So you might think that it's authenticated, but the error will usually come up whenever you try to access the actual values inside of the variables. And so then you can see that we've got this mirrors plot of Hurricane Milton, roughly almost a day after peak strength. And here you can actually see that there are some spots that are blanked out, which could be either off-scale low or high values, which correspond to this extremely high amount of precipitable water, nearly 8 inches of water per column, which just an incredible amount of moisture that Milton brought to the Florida coast. All right, so we've gotten through those, and now what we want to do is go through that really interestingly structured TCIE collection in a slightly different way. So we've queried both the TROPICS 3 and 6 CubeSats because we want to make sure that we can get as much coverage as we can, but you'll notice that we might not get full coverage. That's not an issue. We are going to be prompted once again for our Earthdata login. So I'm going to enter that. And now what we're going to do is use earthaccess to actually stream the entire granules into our notebook session. And you can see that that's running here. Something you will also note is that because they're coming from public cloud endpoints, we can run this in parallel. If you try to run parallelization on those earlier on-premises OPeNDAP queries that we have, you will be rate limited. But we're currently working on migrating a lot of these collections from our on-premises servers over to the cloud. And I can touch briefly on that once we're done with this notebook. After that, we create this helper function, which will extract this beginning date and beginning time attribute and turn those into actual dimensions that we can sort this data set by in a single X-array data set. X-array is simply just a way to load data of different file types and formats into a single object in Python that you can perform different routines on, including regridding, averaging, resampling, and so on. And so this takes about 2 minutes to run, which is not a problem. I'm just going to go ahead and let that run. And I join you. I would like to, invite you all to join this, to run this with me. But once you get that running, you will see in this final cell that we select Hurricane Milton by its storm number. Keep in mind that this query can capture TCIE tracks for different storms. So we only want Hurricane Milton. And we wind up with this plot here, which is a time series of our sea level pressure and max winds. And you can see here that on the day of October 9th, we get this big pressure drop almost down to 930 millibars, which is associated with this huge spike in max winds. And that's pretty typical with a eyewall replacement cycle, where the eyewall will actually become more symmetrical due to pressure deepening, and subsequently you get a higher conservation of angular momentum and a higher velocity of winds, especially as you get through closer to the center of the eyewall. So that is pretty much it for this Jupyter Notebook. And it looks like we're just at about 2 o'clock. Again, I'm sorry to keep most of this time from all of you for questions. And so with that being said, let me go ahead and give it back to Kristen.
Everybody. Thanks, Chris, for that really great demo. Every time I hear it, I think I learned something new. But to wrap up, the datasets that we host on the GES DISC support analysis of high impact events, including Hurricane Milton, which was one of the most intense hurricanes on record in the Atlantic Basin. And I have the timeline that we showed at the beginning of the presentation up here to kind of wrap things up. And so the TROPICS mission CubeSats provide really spatial and temporal high-resolution data that enable users to visualize thermodynamic and precipitation structure of Hurricane Milton and other tropical cyclones. And using the data sets that we have at the GES DISC, we were able to sort of hit all of the milestones of Milton. We were able to capture them. One thing that is not captured is TROPICS has the ability to see convection over land. And so one great analysis undertaking would be to look at Chris's demo and change your rectangular spatial subset of interest to overland, perhaps when Milton made landfall, and you can even see the convective structures associated with the tornado outbreak that was subsequent to Milton making landfall. Additionally, I want to reiterate that understanding the data processing levels and the nuances between the different levels, as well as the structure of the data itself, is crucial to successful data usage sessions from the data sets that we host at the DAC. And using the data in a Google Colab Jupyter Notebook format can allow users to conduct their own analyses for their own research purposes. And GES DISC hosts a suite of tutorials to guide users through finding and accessing our diverse data sets. And here, as promised, is a slide of information, links, and documentation, including the tools used today, Giovanni Panoply, the documentation associated with the TROPICS mission and data user guides, and then links for following Chris's demo in your own time if you so choose. So we thank you for your attendance and your time, and we give special recognition to Bill Blackwell and Vince Leslie of the TROPICS mission for their participation in this, as well as credit to my colleagues Lauren Hilbeaton and Ariana McDermott for the great imagery that they helped work up that we included in this slide. in this slide deck. And finally, I am the Tropics point of contact at the GES DISC, so I have my email listed here, as well as we have the GES DISC help desk, which users can specify which data product they need help with. And if your data product is Tropics or carbon related, this email will end up to me as well. So thank you for your time.
Okay, at this point, we're going to transition to our Q&A session, which will go to 3:15 since we are a little bit late wrapping up the content itself. And so currently, also we've got our Q&A panelists on the line. Currently, I don't see any questions. There are quite a few notes that were taken by one of our participants in the Q&A panel. So if anybody has any questions, please enter those into the Q&A panel. You should see that on the right side of your screen, and I'm going to open up the final polling questions as well. Let's see here. All right, everybody. So the final polls are opened up. Does anybody have any questions? You should take advantage of the fact that we've got one of the Tropics instrument scientists on the line here, and also the principal investigator. So any questions for our science team members or from our speakers at the Goddard DAC? Okay, perfect. Here we go. Let me get started here. Give me just one moment here. Now I'm seeing some questions coming in. All righty. I got to scroll down a bit, everybody. Thanks so much. Okay, so are the citations or DOIs for the subsets of the data we query from the web UI provided anywhere?
Hi, thanks for asking. Yes, certainly. We provide both the citations and the DOIs on the dataset landing pages. And so if you were to go on our website, disc.gsfc.nasa.gov, and search your Tropics data of interest, on the landing page, you will find what you're looking for. And I believe the links are up here above as well. Thanks to Jennifer and Joseph for copying them here.
Well, thanks so much, Kristen. So the next question is, would there be any opportunity for a follow-up webinar touching on the metadata that may have been missed potentially? And I encourage also this participant to add that as a comment in the optional polling questions. I think we have a question that addresses, what future topics might you want to hear about. So please feel free to also note that in the polling questions as well. Does anybody have anything to add to that or in response to that?
Chris, maybe you can speak upon our CMR and how that relates to the metadata for the products.
Yeah, so the metadata can be, we try to make it unified. And so the metadata will have DOIs in it. It'll have various links. We have a couple of different CMR products like UMM-VAR that actually contain the lists of the variables and even the units for those. But those go a little bit beyond kind of the scope of what we're looking at. And in the actual Earthdata search tool that you saw, the CMR is simply just the repository containing all of those metadata records. And I think that answers your question.
Well, thank you so much, Chris. If there's additional follow-up, please feel free to add that in the Q&A. And I did see another question here. If you could give me just one moment here. Okay, thanks for bearing with me. Had to do with stack.
I think another thing just to note is, again, I would just recommend that if you're looking for things like citations or DOIs, to consult the dataset landing page. And if you need to access those things programmatically, then I would go through the content metadata repository.
Okay, thank you so much. So we've got a couple additional questions. So the first one is, do you also support catalog search via Stack?
I can answer that, and the answer is yes, but only for a few of our collections. I think that someday we will look to expand CMR stack a little bit more into some of our other collections, but for many of them, it's not available. I can see if there's a document that I can share with you that lists out which ones are available.
Well, that would be great. Thank you so much, Chris. And our next question is perhaps a little bit outside of the scope of this webinar, but I'm going to pose the question anyway, since we have our science team members here as well. What caused the severe storm surge from Hurricane Helene?
So again, this is a webinar focused on Hurricane Milton. However, Jim did give a great overview of the sort of upwelling effects that very strong hurricanes can have as they pass through the Gulf and stir the waters. And so perhaps Hurricane Helene stirred up the waters and was able to carry that onto shore when it made landfall. But if there are other people, Vince or Bill, that wear more of a meteorology hat than I do, have any input, that
Actually, I can comment on that too. One of the
great.
main reasons Helene had a big storm surge, though fortunately that storm surge went into an area that wasn't nearly as populated as where Milton went, was it was moving so fast. You know, it didn't slow down when it hit the coast, and basically all that forward momentum was caught up as part of the storm's energy when it hit the coast, and it kept going. I can't remember the exact track, but I think Helene was still at hurricane strength well into Georgia.
Hey, thank you so much for that additional input. And I didn't know if perhaps Dr. Leslie or Dr. Blackwell wanted to weigh in as well. And if not, then I'm going to actually move on to a question that was posed in the chat by one of our speakers. Just pausing for a moment if anybody wanted to provide any more information.
I was just going to agree with Jim that was a freight train of a storm that just slammed in with high winds and a lot of rain, and tornadoes started to creep up.
All right, well, thank you so much. So the next one is, are there any plans to create global level 3 data products for TROPICS, even though I imagine it might be complex to do?
Let's see. Yeah, so we are, and I defer to Vince on this too. We are planning some level 3 products, and I guess that is not a priority at the moment. But we're in extended mission operations now, but it's something that we'll turn to pretty quickly. But I think I'll say that we have aspirations to do that. And if Vince wants to add to that, he can.
No, that's summed it up well.
Thank you so much, Vince, and thank you.
I asked
Bill.
that because that's what we put into Giovanni, so it'd be nice to have.
All right.
Duly noted. We agree.
Thanks.
Thank you so much. Okay, our next question is, could conditions in the near future be similar to those that caused Hurricane Milton? Will this be the new normal in the Gulf of Mexico?
So this is a sort of far-reaching question. No one can speak on the future, certainly, but when I read this question, I was curious on Bill and Vince's take on this, as they have looked at tropical systems with the TROPICS data. I wanted to see what their take was and any trends they're seeing in some of the hurricane seasons that TROPICS is able to observe.
Yeah, it's a great question, something that we're looking into. So the one nice thing about TROPICS is we have, the data record now to almost start to divine, information on trends and things like that. So we're looking at it. I don't think we have any conclusions on that particular question yet, but I think we will pretty soon, given that we've had, almost 2 years of data now from TROPICS.
Yeah, that's great. Yeah, to be able to discern trends, you need an abundance of data and time. So hopefully that question is more and more addressed as the mission goes on.
Okay, I am looking to see if there are any additional questions. We essentially have time for one more. And then what we'll do, if there are no, I'm just scanning the chat as well. What we'll do is we will leave the virtual meeting space open, but log off from the audio component. Currently, I do not see any additional questions, but certainly if you think of something, please do feel free to add that to the chat or to the Q&A. Again, I'll stay on the line an additional 10 minutes. I wanted to extend my gratitude and thanks to all of you for joining us this afternoon, and to our speakers, Chris Battisto, James Acker, and Kristen Morgan, and then finally to our two Q&A panelists, Vince Leslie and William Blackwell, and last but certainly not least, my co-host, Joseph Smith, and also our team science writer. So thanks to all of you for joining us this afternoon. And I'll leave the virtual meeting space open. We really do appreciate your feedback on the polling questions as well. That helps to guide decisions when determining future topics for webinars, and really helps us to better understand data user needs. And so thanks so much, everybody. And with that, we will log off from the audio component, and I will leave the virtual meeting space opened. All right, and just a quick pitch. Coming up, this might not be your discipline or field, but coming up in a couple of weeks, we will have our second ISAT 2 data training webinar, which will focus on the vegetation height canopy products. And so I expect to have that event announced on earthdata.nasa.gov in the next couple of days. So stay tuned. All right, well, thanks everybody. Take care now. We hope to see you at an upcoming webinar.
Thanks, everybody.
All right, bye-bye.